We present rotationally equivariant 3D object detection. Recently, rotational equivariance has been a strongly desired property in the 3D learning community. It has proven to be useful in single-object 3D tasks, including shape classification, reconstruction, and pose estimation. But existing methods are unsuitable for 3D object detection because their designs only provide equivariance regarding entire scene-level inputs. They ignore the fact that rotational symmetry has its own spatial support. We argue that the spatial support in object detection should be object level rather than scene level. We will demonstrate object level rotation equivariance by rotating a chair in a room. As shown in the reference figure, we expect that the chair's bounding box should rotate along with it, the box shape should not change, and all other boxes should stay still. However, a state-of-the-art detection model does not meet any of these expectations. Our method equips this model with object-level rotation equivariance, leading to much more stable and better outcomes. Collectively, when we rotate the whole scene with all objects moving, we expect the outcomes to look like the reference figure. But once again, the existing method leads to unstable predictions. With the object-level equivariance provided by our method, the outcomes are significantly improved. Our technical goal is to equip existing 3D detectors with object-level rotation equivariance. Our approach is a plug-and-play design which is applicable to existing 3D detectors. A major challenge is context aggregation. Nearby objects provide useful information, co-occurrence, for detection, but we don't want them to break the detector's object-level equivariance. Our solution to these challenges will be a simple design we call equivariance suspension. We will introduce it a bit later. To achieve our technical goal, we ground our method on the popular bottom-up design. Let us quickly review the building blocks in this design. Given an input point cloud, a bottom-up detector extracts a dense set of seed point features. It then aggregates larger spatial context to produce a sparse set of region features. Examples include voting, bird-eye view convolution, ROI pooling, etc. Finally, a proposal module takes a region feature and proposes oriented bounding boxes. Our approach, EON, follows this bottom-up design. To restrict the spatial support for rotation equivariance and to incorporate context, we propose equivariance suspension. We extract equivariant features in the seed feature extraction stage. The seed features are expected to approximately correspond to an object level. We suspend equivariant computation here by explicitly decomposing the equivariant features into object frame invariant features and the orientations of these object frames. We aggregate the invariant features just like the original module does. The orientations are retained. Thus, we aggregate context information in the object frame features, which do not influence equivariant computation. Finally, we generate boxes in the object frame and rotate them back to the scene frame. In this way, the object-level equivariance is resumed. In our experiments, we show that our approach is applicable to indoor and outdoor scenes, various detector designs, and different backbones. For indoor scenes, we evaluate our method on ScanNet v2 with both VoteNet and a transformer-based model. Here we show qualitative results comparing VoteNet and our EON VoteNet. In the top row, the chairs are placed in an unusual orientation. In the bottom row, we show a crowded scene with many objects of the same category. In the top row, we show another cluttered scene. In the bottom row, we show that our method can perform well with large, thin objects. In the top row, we show detection of medium-sized, thin objects. In the bottom row, we show scenes with small objects. For outdoor scenes, we evaluate our method on Kitty 3D with PointRCNN. Our method improves detection performances for all these settings. Thanks for watching.